Hi guys, tonight we're going to take an extraordinary journey 1 billion years into Earth's future. We're not talking about centuries or even millennia. We're talking about a span of time so vast that it will completely transform our planet in ways both fascinating and terrifying. If you enjoy these epic deep dive sleep stories that explore the far reaches of time and space, hit that like button and subscribe for more. And drop a comment letting me know what time it is where you are and where you're listening from. I always love hearing from you night owls around the world. Alright, let's begin. Imagine standing on a beach tonight, watching waves crash against the shore under a sky filled with familiar constellations. The moon hangs overhead, its cratered face unchanged from what our ancestors saw 1 million years ago. Now stretch your mind forward, not just centuries or millennia, but 1 billion years into the future. This isn't science fiction. This is the extraordinary story of what Earth's deep future might hold, written in the language of physics, geology, and evolutionary biology. 1 billion years represents a span of time so vast it challenges human comprehension. To put this in perspective, 1 billion years ago, complex multicellular life was just beginning to experiment with its first tentative forms. The oldest fossils of animals with hard shells date back only 600 million years. The dinosaurs lived a mere 65 million years ago, a geological blink of an eye. If Earth's entire 4.5 billion year history were compressed into a single 24-hour day, 1 billion years would represent more than 5 hours of continuous change, transformation, and evolution. As we embark on this journey through deep time, the first thing to understand is that Earth itself will be dramatically different. Our planet orbits a star that has been growing steadily brighter throughout its 10 billion year lifespan. The Sun today produces 30% more energy than when Earth first formed, and this brightening will continue. Over the next billion years, solar luminosity will increase by another 10%. This might seem modest, but the consequences will be profound and irreversible. The additional solar energy, equivalent to adding 14 trillion watts of power continuously across Earth's surface, will fundamentally alter our planet's climate system. Today, Earth receives approximately 1,366 watts per square meter of solar energy at the top of the atmosphere. In 1 billion years, this figure will reach roughly 1,500 watts per square meter. The extra energy will drive atmospheric temperatures higher, accelerate evaporation rates, and trigger a cascade of feedback mechanisms that will transform every aspect of Earth's environment. Water vapor is a powerful greenhouse gas, more potent than carbon dioxide in its ability to trap heat. As global temperatures rise, more water will evaporate from oceans, lakes, and rivers. The warmer atmosphere will hold this additional moisture, creating an intensifying cycle of heating and evaporation. Climate models suggest that average global temperatures could rise by 8 to 10 degrees Celsius over the next billion years, even without considering other greenhouse gases. This warming will be uneven, with polar regions experiencing the most dramatic changes, potentially seeing temperature increases of 15 to 20 degrees Celsius. The hydrological cycle will enter a state of hyperdrive. Precipitation patterns will become increasingly extreme, with some regions experiencing torrential monsoons while others face permanent drought. The Amazon rainforest, currently home to approximately 10% of all known species, and producing 20 billion tons of water vapor daily, may gradually transform from a lush tropical ecosystem into something resembling a savanna or even desert. The Congo Basin, covering 2 million square kilometers and supporting over 75 million people today, faces a similar fate. Ocean levels will initially rise as thermal expansion occurs, and remaining ice sheets melt completely. The West Antarctic ice sheet alone contains enough water to raise global sea levels by 3.5 meters, while the Greenland ice sheet holds 7.5 meters worth of potential sea level rise. But as temperatures continue climbing and atmospheric water vapor increases, a paradoxical process will begin. The upper atmosphere will become so laden with water vapor that significant amounts will begin escaping to space through a process called atmospheric escape. This process occurs in Earth's exosphere, the outermost layer of atmosphere extending from about 700 kilometers to 10,000 kilometers above the surface. Here, water molecules dissociate into hydrogen and oxygen under the influence of intense solar ultraviolet radiation. The light hydrogen atoms, moving at speeds of several kilometers per second due to the extreme temperatures, can achieve escape velocity and drift away into space forever. Earth currently loses about 3 kilograms of hydrogen to space every second, but this rate will accelerate dramatically as water vapor concentrations increase. Over hundreds of millions of years, this atmospheric escape will cause Earth's oceans to gradually shrink. The Pacific Ocean, currently holding 710 million cubic kilometers of water, will begin a slow retreat. Coastal cities that once thrived along ocean margins will find themselves increasingly inland. The Mediterranean Sea, already largely enclosed and prone to evaporation, may disappear entirely within 500 million years. The Atlantic Ocean, containing 310 million cubic kilometers of water, will become shallower and more saline as its volume decreases. Continental drift will continue reshaping Earth's surface throughout this billion-year period. The Atlantic Ocean currently expands at a rate of 2.5 centimeters per year as the mid-Atlantic ridge spreads the seafloor. Over 1 billion years, this seemingly small rate will move the continents roughly 25,000 kilometers relative to each other. North America and Europe, currently separated by approximately 4,000 kilometers across the Atlantic, could be nearly 6,000 kilometers apart. The Pacific Plate moves northwest at 7 centimeters per year toward the Eurasian Plate. In 1 billion years, this movement will carry the plate 70,000 kilometers from its current position, dramatically altering the Pacific Ring of Fire and the distribution of volcanic activity. The Himalayan mountain range, still growing at a rate of 5 millimeters per year as India continues pushing into Asia, will have risen an additional 5,000 meters, creating peaks potentially exceeding 15,000 meters in elevation. These tectonic movements will create new mountain ranges, open new ocean basins, and fundamentally alter global weather patterns. The position of continents relative to ocean currents determines much of Earth's climate. The Gulf Stream, which currently carries 65 million cubic meters of warm water per second from the Caribbean toward Europe, could be disrupted or redirected entirely. Similarly, the Antarctic Circumpolar Current, the world's strongest ocean current moving 135 million cubic meters of water per second around Antarctica, will be affected by changing continental positions and ocean depths. Volcanic activity will remain a major geological force throughout this period. Earth's interior contains approximately 4 billion cubic kilometers of magma in various forms, with temperatures reaching 5,000 degrees Celsius at the core boundary. The planet loses roughly 44 trillion watts of heat continuously through volcanic activity, plate tectonics, and conduction. This heat engine will continue driving geological processes for billions of years beyond our billion-year timeline. Supervolcanic eruptions, events capable of ejecting more than 1,000 cubic kilometers of material, occur roughly every 50,000 years in Earth's history. Over 1 billion years, Earth might experience 20,000 such eruptions. The Yellowstone supervolcano, sitting atop a magma chamber containing 25,000 cubic kilometers of partially molten rock, represents just one of several potential supervolcanic systems that could shape the planet's future. A single supervolcanic eruption can lower global temperatures by several degrees Celsius for decades by injecting millions of tons of sulfur compounds into the stratosphere. The carbon cycle, fundamental to all life on Earth, will undergo dramatic changes during this billion-year span. Currently, the atmosphere contains approximately 850 billion tons of carbon in the form of carbon dioxide, while the oceans hold 38,000 billion tons of dissolved carbon. As temperatures rise and ocean chemistry changes, the delicate balance between atmospheric and oceanic carbon will shift dramatically. Higher temperatures will accelerate chemical weathering of rocks, a process that currently removes about 200 million tons of carbon dioxide from the atmosphere annually. Silicate rocks react with carbon dioxide and water to form carbonates, effectively storing atmospheric carbon in solid form. However, the increased weathering rate will be offset by accelerated volcanic outgassing and the decreased solubility of carbon dioxide in warmer oceans. Plant life faces extraordinary challenges in this future Earth. Photosynthesis, the process that has supported virtually all complex life for over 3 billion years, operates efficiently within a narrow temperature range. Most plants today photosynthesize optimally between 20 and 35 degrees Celsius. As global temperatures rise 8 to 10 degrees above current levels, vast regions of Earth will become too hot for conventional photosynthesis. The Amazon rainforest currently sequesters approximately 2 billion tons of carbon dioxide annually through photosynthesis, involving roughly 400 billion individual trees. As temperatures rise beyond the thermal tolerance of tropical species, this massive carbon sink will transform into a carbon source, releasing stored carbon back to the atmosphere and accelerating warming further. The boreal forests of Canada and Russia, containing approximately 35% of global forest carbon stocks, will face similar challenges as temperature zones shift poleward. However, life has demonstrated remarkable adaptability throughout Earth's history. During the Paleocene-Eocene thermal maximum 56 million years ago, global temperatures rose by 5 to 8 degrees Celsius within 200,000 years. Life not only survived but diversified rapidly, with mammals evolving into new ecological niches and tropical forests extending to polar regions. Palm trees grew in Alaska, and crocodiles lived near the North Pole when global temperatures averaged 28 degrees Celsius compared to today's 15 degrees. Evolution will continue operating throughout our billion-year timeline, potentially producing organisms adapted to the hotter, more volatile conditions. Plants might evolve enhanced heat tolerance, more efficient water use, or entirely new photosynthetic pathways. Some organisms could develop strategies to exploit the increased energy available in the environment, similar to how thermophilic bacteria thrive in hot springs at temperatures exceeding 80 degrees Celsius. The concept of refugia becomes crucial when considering life's survival strategies. These are small areas where environmental conditions remain suitable for life, even as surrounding regions become inhospitable. High-altitude locations, polar regions, and deep ocean environments might serve as refugia for millions of years. Mount Everest, currently 8,849 meters tall and still growing, will reach over 9,300 meters in 1 billion years, potentially providing high-altitude refugia where temperatures remain tolerable. Ocean depths will remain relatively stable temperature refugia for much longer than surface environments. The deep ocean currently maintains temperatures between 2 and 4 degrees Celsius, even in tropical regions. While surface waters may become lethally hot, depths below 1,000 meters could remain habitable for hundreds of millions of years. The deep ocean contains roughly 97% of Earth's liquid water and hosts unique ecosystems around hydrothermal vents that derive energy from chemical processes rather than sunlight. These deep-sea communities, discovered only in 1977, demonstrate life's ability to thrive in extreme conditions. Hydrothermal vents support ecosystems based on chemosynthesis, where bacteria convert hydrogen sulfide and other chemicals into organic compounds. The tube worms around these vents can reach lengths of 2.5 meters and live for over 300 years without any dependence on photosynthesis. Such communities could persist throughout our billion-year timeline, potentially serving as the foundation for Earth's final evolutionary chapter. Underground environments represent another crucial refugia category. Subsurface ecosystems extend at least several kilometers deep into Earth's crust, hosted in groundwater systems that maintain stable temperatures year-round. These environments currently support diverse microbial communities that could survive surface temperature increases. The Homestake mine in South Dakota harbors living microorganisms at depths of over 1.5 kilometers, where temperatures reach 60 degrees Celsius. Similar deep biosphere communities exist worldwide, containing an estimated 15 to 23 billion tons of carbon in living organisms. As surface conditions deteriorate, evolution might drive life increasingly toward these underground and deep ocean refugia. Over millions of generations, organisms could adapt to entirely subterranean lifestyles, developing enhanced abilities to extract energy from chemical processes, navigate in darkness, and survive in high-pressure environments. The Mexican cavefish, which lost its eyes and pigmentation after adapting to cave environments, provides a small-scale example of how life modifies itself for extreme environments. Atmospheric composition will change dramatically throughout this billion-year period. Currently, Earth's atmosphere contains 78% nitrogen, 21% oxygen, and approximately 400 parts per million carbon dioxide. The oxygen concentration results from billions of years of photosynthesis by plants and cyanobacteria. As plant productivity declines due to extreme temperatures, atmospheric oxygen levels may begin decreasing for the first time in over 2 billion years. The Great Oxygenation Event, which occurred around 2.5 billion years ago, initially poisoned most existing life forms, but ultimately enabled the evolution of complex multicellular organisms. A reversal toward lower oxygen concentrations would fundamentally alter evolutionary pressures and possibilities. Organisms might evolve more efficient oxygen utilization systems, or life might adapt to lower oxygen conditions similar to those that existed for Earth's first 2 billion years. Nitrogen, the most abundant atmospheric gas, will remain relatively stable throughout this period. However, the nitrogen cycle will be disrupted as extreme temperatures affect the microorganisms responsible for nitrogen fixation and denitrification. Currently, biological nitrogen fixation converts approximately 100 million tons of atmospheric nitrogen into ammonia annually, supporting plant growth worldwide. Lightning contributes another 8 million tons of fixed nitrogen yearly through high-energy reactions in the atmosphere. The magnetic field generated by Earth's molten iron core will continue protecting the planet from solar radiation throughout this period, though its strength may fluctuate significantly. Earth's magnetic field currently deflects most charged particles from the solar wind, preventing atmospheric stripping similar to what occurred on Mars billions of years ago. However, the magnetic field has reverse polarity over 700 times in Earth's history, and the field strength has decreased by 15% over the past 2 centuries. Magnetic field reversals typically occur every 200,000 to 300,000 years, though the intervals are highly irregular. During reversals, field strength drops to about 10% of normal levels for several thousand years, allowing increased cosmic radiation to reach Earth's surface. Over 1 billion years, Earth might experience 3,000 to 5,000 magnetic reversals, each creating temporary periods of increased radiation exposure and potential disruption to any remaining complex life. The Moon's gravitational influence will continue shaping Earth throughout this period, though the Moon itself will gradually recede from Earth at a rate of 3 8/10 centimeters per year. Currently located 384,400 kilometers from Earth, the Moon will be approximately 420,000 kilometers away in 1 billion years. This increased distance will weaken tidal forces, reducing tidal ranges and altering coastal dynamics worldwide. Tidal forces currently dissipate approximately 3 7/10 terawatts of energy in Earth's oceans, gradually slowing the planet's rotation and causing the Moon to spiral outward. 1 billion years ago, Earth's day lasted approximately 18 hours, and the Moon appeared much larger in the sky. In our future billion-year scenario, days will lengthen to approximately 25 hours, subtly altering atmospheric circulation patterns and biological rhythms for any surviving life forms. The weakening tidal forces will have profound effects on coastal ecosystems, many of which depend on regular tidal cycles for nutrient distribution, reproduction, and feeding patterns. Intertidal zones, currently among Earth's most productive ecosystems, will shrink as tidal ranges decrease. The Bay of Fundy, famous for tides reaching 16 meters in height, might experience maximum tides of only 12 meters. This reduction affects not only marine life but also tidal energy generation and coastal sediment transport. Human civilization, if it survives in any recognizable form, will face challenges beyond imagination during this billion-year timeline. Current human population of approximately 8 billion people depends on agricultural systems that produce about 4 billion tons of food annually. As temperatures rise and precipitation patterns shift dramatically, traditional agriculture will become impossible across vast regions of Earth. The concept of habitability zones will shift continuously throughout this period. Currently, the most densely populated regions of Earth lie between 30 and 60 degrees latitude in both hemispheres, where temperatures remain moderate and precipitation supports agriculture. As global temperatures rise, the habitability zone will shift toward the poles, potentially making Antarctic and Arctic regions more suitable for human habitation than current temperate zones. Antarctica, currently covered by ice sheets containing 24 million cubic kilometers of ice, will gradually transform into a temperate continent. The Antarctic landmass covers 14 million square kilometers, roughly equivalent to the combined area of the United States and Mexico. As ice sheets melt and temperatures moderate, this continent could support human civilization for hundreds of millions of years after other continents become uninhabitable. Technology development over such vast timescales could enable humanity to adapt to changing conditions through artificial environments, genetic modification, or even planetary engineering. Current global energy consumption approaches 20 terawatts annually, mostly from fossil fuels. Future civilizations might harness geothermal energy from Earth's interior, which provides a continuous 44 terawatts of power, or develop space-based solar collection systems to manage increasing solar radiation. The possibility of terraforming or climate management becomes relevant over billion-year timescales. Current geoengineering proposals include solar radiation management techniques that could reflect excess solar energy back to space. Stratospheric sulfur injection, inspired by volcanic eruptions that cool global temperatures, could theoretically counteract solar brightening effects. However, such interventions would require continuous maintenance and massive technological infrastructure over geological timescales. Underground cities represent another adaptation strategy for extreme surface conditions. Current underground facilities, such as the Coober Pedy opal mining town in Australia, where residents live underground to escape extreme heat, demonstrate the feasibility of subterranean habitation. Future underground cities could be constructed in geologically stable regions, utilizing geothermal energy and recycled atmospheric systems to support large populations. The biological changes occurring over this timeline will reshape fundamental aspects of life on Earth. Evolutionary pressures from extreme heat, altered atmospheric composition, and changing ocean chemistry will drive rapid speciation and adaptation. Species currently considered highly successful may disappear entirely, while others may evolve into forms unrecognizable by today's standards. Microorganisms will likely dominate Earth's biosphere throughout this period, as they have for most of the planet's history. Bacteria and archaea demonstrate remarkable adaptability to extreme conditions, thriving in environments ranging from boiling hot springs to highly acidic waters to radiation-intense locations. Some thermophilic bacteria can survive temperatures exceeding 120 degrees Celsius, suggesting that microbial life could persist even as surface temperatures reach lethal levels for current complex organisms. The emergence of entirely new metabolic pathways becomes probable over such extended timescales. Life has previously invented photosynthesis, respiration, fermentation, and numerous other energy conversion processes through evolutionary experimentation. Future organisms might develop methods to directly utilize thermal energy from hot environments, extract energy from electromagnetic radiation beyond the visible spectrum, or process entirely new chemical compounds that accumulate in the altered atmosphere. Symbiotic relationships, where different organisms cooperate for mutual benefit, may become increasingly important as environmental stresses intensify. Current examples include lichens, which represent partnerships between fungi and photosynthetic organisms that can survive in extremely harsh environments including bare rock surfaces and Arctic conditions. Future symbioses might involve multiple organisms working together to cope with heat stress, water scarcity, and altered atmospheric conditions. Ocean chemistry will undergo fundamental changes that affect all marine life. As atmospheric carbon dioxide concentrations increase and temperatures rise, ocean pH will continue decreasing through a process called ocean acidification. Current ocean pH averages 8.1, down from approximately 8.2 in pre-industrial times. Continued acidification could lower ocean pH to 7.8 or below, creating conditions corrosive to shell-forming organisms. The thermohaline circulation system, often called the ocean's conveyor belt, transports approximately 15 million cubic meters of water per second between ocean basins, distributing heat and nutrients globally. This circulation depends on temperature and salinity differences between water masses. As polar ice melts and temperature gradients decrease, thermohaline circulation may weaken significantly, or even shut down entirely, fundamentally altering marine ecosystems and global heat distribution. Coral reefs, currently supporting approximately 25% of marine species, despite covering less than 1% of ocean area, face extinction within the first few 100 million years of our timeline. Coral organisms exist in symbiosis with photosynthetic algae that cannot survive prolonged temperature increases above their thermal tolerance. The Great Barrier Reef, stretching 2,300 kilometers along Australia's coast and supporting over 9,000 species, represents an ecosystem type that may not survive Earth's hot future. However, deep-sea ecosystems could expand as surface conditions deteriorate. The deep ocean, currently less productive than surface waters due to limited sunlight and nutrients, might become the primary habitat for complex life. Hydrothermal vents, cold seeps, and other chemosynthetic ecosystems could serve as the foundation for extensive deep-sea communities that develop over millions of years without any dependence on surface photosynthesis. Geological processes will create new opportunities and challenges throughout this period. Volcanic activity will continue generating new landforms and potentially creating temporarily habitable zones. Large volcanic eruptions can cool regional or global temperatures for years or decades, potentially providing brief respites from the overall warming trend. The Toba supervolcano eruption 74,000 years ago lowered global temperatures by several degrees for approximately 6 years, demonstrating volcanoes' potential to create temporary climate refugia. Mountain building through tectonic processes will continue creating high-altitude environments where temperatures remain more moderate than at sea level. The formation of new mountain ranges could provide corridors for species migration and evolution, similar to how the Himalayas currently support diverse ecosystems at different elevations. At 5,500 meters elevation, temperatures average approximately 30 degrees Celsius below sea level temperatures, potentially making high mountains habitable long after lowlands become uninhabitable. Asteroid impacts, while unpredictable, could significantly influence Earth's trajectory during this billion-year period. Statistical analysis suggests Earth experiences impacts from kilometer-sized asteroids approximately every 500,000 years, and from 10-kilometer asteroids roughly every 100 million years. Over 1 billion years, Earth might face 2,000 large asteroid impacts, each capable of causing temporary global cooling through dust injection into the atmosphere. The Chicxulub impact 66 million years ago, which contributed to dinosaur extinction, involved an asteroid approximately 10 kilometers in diameter that released energy equivalent to 10 billion times the power of all nuclear weapons ever built. While devastating to existing ecosystems, such impacts also create opportunities for evolutionary innovation by eliminating dominant species and opening new ecological niches. Solar evolution will ultimately determine Earth's fate beyond our billion-year timeline. Current stellar evolution models predict that the Sun will continue brightening for approximately 5 billion more years before beginning its transformation into a red giant star. However, the critical threshold for Earth's habitability occurs much sooner, within the next billion to billion-and-a-half years, when solar luminosity increases sufficiently to trigger runaway greenhouse effects. The runaway greenhouse effect occurs when atmospheric water vapor concentrations reach levels where additional warming causes more evaporation, which causes more warming in an unstoppable positive feedback loop. Venus likely experienced this process early in its history, resulting in surface temperatures now reaching 460 degrees Celsius, despite receiving only twice as much solar energy as Earth. Climate models suggest Earth will reach the runaway greenhouse threshold when solar luminosity increases by approximately 10 to 15% above current levels. This increase will occur within the next 800 million to 1.5 billion years, marking the beginning of Earth's final transformation toward Venus-like conditions. Surface temperatures will eventually reach over 100 degrees Celsius globally, making liquid water impossible anywhere on the planet's surface. However, this timeline assumes no technological intervention or adaptation. Advanced civilizations might develop methods to manage solar energy input through space-based solar shades, atmospheric engineering, or even stellar manipulation. The energy requirements for such projects would be enormous, potentially requiring the entire energy output of human civilization for thousands of years, but they remain theoretically possible. The concept of planetary migration also becomes relevant over these timescales. While beyond current technological capabilities, future civilizations might develop methods to gradually move Earth's orbit outward to compensate for increasing solar luminosity. This would require changing Earth's orbital energy by approximately 10 to the 42nd power joules, equivalent to the total energy Earth receives from the Sun over 10 million years. Alternative strategies might focus on preserving life through other means. Generation ships capable of supporting human civilization for thousands of years could transport Earth's biological heritage to other star systems. The nearest potentially habitable exoplanet, Proxima Centauri b, lies 4.2 light-years away and could theoretically be reached by advanced propulsion systems within several thousand years of travel time. Seed ships carrying genetic information and artificial intelligence systems could establish Earth-derived ecosystems on distant worlds, ensuring the continuation of terrestrial life even after Earth becomes uninhabitable. Current data storage technology can theoretically encode the complete genetic information of millions of species in devices weighing only kilograms, making such preservation strategies feasible with sufficiently advanced technology. Throughout this billion-year journey, Earth will witness the rise and fall of countless species, the formation and erosion of mountain ranges, the opening and closing of ocean basins, and the continuous dance of evolution, responding to changing environmental conditions. The planet that emerges at the end of this timeline will bear little resemblance to today's Earth, yet it will still be the same world that has hosted life for over 3.5 billion years. The story of Earth's next billion years is ultimately a story about life's extraordinary persistence and adaptability. From the first microorganisms that survived in an oxygen-free atmosphere, to the complex ecosystems that recovered from mass extinction events, life has repeatedly demonstrated its ability to find ways to survive and thrive under the most challenging conditions. While the specific forms that life takes during Earth's hot future remain unpredictable, the fundamental creativity and resilience of biological systems suggest that some form of life will persist far longer than we might initially imagine. This deep time perspective reveals both the fragility and the durability of our planetary home. While human timescales make 1 billion years seem infinite, it represents merely the next chapter in Earth's continuing story. Understanding this timeline helps us appreciate the precious stability of our current environment, while recognizing that change, adaptation, and transformation are the only constants in our planet's long and remarkable history. The Earth of 1 billion years hence will be a world transformed, but it will still be our world, carrying forward the unbroken chain of life that connects us to the very first living cells and extends toward possibilities we can barely imagine.